In this session on the special senses, we're going to be thinking about the ears with relation to balance or equilibrium. At the end of the session, you should be able to describe the basic structure and function of the ears with relation to balance. And it's the vestibular apparatus that is important for that balance, and it helps to detect the position and motion of the head. And in particular, the two little regions that it has, or areas it has, you have the vestibular apparatus, which is the whole region. And then you've got within this the utricle and saccules. That's one little area that we'll talk about, and that's to do with movement of the head, linear motion forwards or forwards and backwards and up and down or tilting the head. And then you've got the semicircular canals, which is all about rotation. And each of these has got fluids in them. We'll talk about those fluids, the endolymph, and that fluid moves past an ampulla in some of these cases, which has got little hairs in it, which move with the swaying of the perilymph, or of the endolymph rather. So it's a bit like movement of seaweed in the waves. This is present in the inner ear, and you can also see in this image, just while I remember actually, you can see the oval window, the round window, and the cochlear and the auditory nerve, which make up the other part of the ear, the internal ear, to do with hearing, of course. So it's present in the inner ear, and it coordinates head movements with eye and postural movements. And it contains, as we talked about, the fluids, so the endolymph and the perilymph, and hair cells that move as the head moves. And as I've already said, it consists of two sets of structures. So it's got the semicircular canals, and that's about dynamic equilibrium. And these are all at right angles to each other. So you've got the three different right angles, and they monitor changes in head rotation. So that might be spinning on the spot, or doing a cartwheel, or a tumble turn, for example, is the kind of thinking if you're thinking about the types of motions. And then you've got the otolith organs, which are the utricle and the saccule. And these are to do with static equilibrium. And as I said, they help to monitor linear acceleration. So that can be linear, moving forwards or backwards, or up and down if you're in a lift, for example. And that's all with relation to the position of the head with respect to gravity. So it's also about tilting your head forwards or tilting your head backwards. So now we'll have a little bit of a look at the semicircular canals. So they detect rotational or angular acceleration or deceleration of the head. The semicircular canals lie at right angles to each other, so there are your three semicircular canals, and they lie at right angles, so the three separate right angles that you can have. If you use your hands together and just point them in the three different directions that you can have, you can kind of work out what that is, because I can't do it in front of you, otherwise I would. And if we're also taking a look at it, the acceleration or deceleration during head rotation causes fluid movement in at least one of these canals. So here you can see the fluid movement. And that, of course, the fluid lags behind the head initial movement, and that delayed fluid movement causes the hairs to bend. So really what's happening is the semicircular canals are detecting the starting or stopping of rotation. So, for example, the starting and stopping of spinning, turning the head, or somersaulting. And the way to think of it is the fluid, in essence, is moving in the opposite direction to the head movement, because the endolymph is left behind as you start to rotate your head. Therefore, the fluid is shifted in the opposite direction relative to the movement, similar to your body tilting to the right as a car in which you're riding suddenly turns to the left. And this causes the cupula, which you can see there, to lean in the opposite direction of the head movement, bending the sensory hairs embedded in it. But if your head continues at the same rate in the same direction, the endolymph catches up and moves in unison with your head, so that the hairs go back to the upright position. And when your head slows and stops, the reverse situation occurs. So, like we've already said, and I've just said this, if your head continues at the same rate in the same direction, the fluid and the head are basically moving at the same time and at the same speed, the hairs go back in the upright position. And your body, in that respect, doesn't think, or your equilibrium, your vestibular apparatus doesn't think that there's any movement going on, but of course your eyes do, so you're still aware of it. Don't forget you have different senses working at the same time, and your joints are still moving, so you have different senses. When your head slows and stops, the reverse situation occurs. So if we're looking at this pirouette, you can see here she is, she's pirouetting around, and when she's not moving, the cupula's nice and upright, and then you get the flow of endolymph moving one way, and the flow of moving, and as you slow down, the flow of endolymph moves in the opposite direction. So at rest, the copula stands upright, along with the associated cilia in there, and you've got the kinocilium and the sterocilia. So the kinocilium is the bigger one. And during the rotational acceleration, the endolymph moves inside the semicircular canals in the direction opposite of the rotation. Remember, it lags behind due to inertia. So the endolymph flow bends the cupula and excites the hair cell. As the rotational movement slows, the endolymph keeps moving in the direction of the rotation, bending the cupula in the opposite direction from acceleration and inhibiting the hair cells. As you're moving in one way and then the other, these are mechanically gated ion channels because the hairs are moving, so they're mechanical, they're pressure changes, and you get depolarization going one way and hyperpolarization going the other way. So you always know which way you're flowing because you're getting different signals coming through, more or less action potentials. So the fluid movement causes either depolarization or hyperpolarization, depending on the direction of the fluid movement. So the cilia of the hair cells are deflected by the fluid movement. They pull on the mechanically gated ion channels. Those channels open or close depending on the direction of fluid flow, and you therefore get hair cell depolarization or hair cell hyperpolarization. You get that synapse with the vestibular nerve, and that information is transported to the cerebellum because you're thinking about smooth movements. Your cerebellum needs to know where your head is in space. It goes to the brainstem for any reflexes, and it goes to the cerebral cortex for conscious awareness of where your head actually is. But it's important to remember the semicircular canals detect changes in the rate of rotational movement, in other words, acceleration or deceleration, but they don't respond when your head is motionless or moving in a circle at a constant speed. So that's your semicircular canals. Relatively simple. Now you've got your otolith organs, okay? So these are the ones that are involved in linear movement and your head position. So linear movement, walking forwards or backwards or going up or down in a lift, for example, but also if you're tilting your head forwards or backwards. So the otolith organs, so here they are, that's your utricle and your saccule. They provide information about the position of the head relative to gravity. So that's your tilting backwards and forwards, but also in relation to linear movement. So we're thinking about a static head tilt and we're moving in a straight line. Like I said, it consists of your utricle and your saccule. And if we're looking at the otoliths themselves, these otolith layers have got calcium carbonate on the top of them, suspended in a gel layer, and it's much, much heavier. And the hairs of the receptor cells also protrude into that gelatinous layer. So you can see that gelatinous layer there, and you can see the hair cells protruding into it. So you've got your kinocilium and your sterocilia as well. And these movements any movements displace the hairs and results in a receptor potential. Remember what the otoliths are doing? They're basically adding weight to the gelatinous layer, making the layer heavier with more inertia. And so just so that you're aware of where they are, when you are upright, your hairs in your utricle are also upright. And the hairs in your saccule are horizontal. So what I want you to think about, imagine you're standing upright right now. I want you to tell me which set would respond. Would your utricle respond to a lift going up or down, or would your saccule respond to a lift going up or down? Well, hopefully you worked out it was the saccule, because when you're standing upright, they are in the horizontal plane. So therefore, if you start going up or down in a lift, those hairs will move correspondingly. And likewise, because the utricles are upright in the standing position, they will respond when you move forwards or backwards, so your linear movements. So this is what we're going to be talking about. We've done an example already, but we'll do utricle as an example, and we're thinking about tilting. So if you tilt your head in any direction, the hairs will bend in the direction of the tilt due to gravity. So if we're taking a little look at this image here, you can see this guy, he tilts his hair neutral position, and you can see the utricles hairs are upright, and you see then he bends his head backwards, and you can see that the hairs bend backwards. So the otolith moves downhill because it's heavy, remember, so it's responding to gravity, so it's pulling everything downhill, and it's distorting the hairs because that is a gel. Okay, so remember that's a gel layer. You've got a heavy otolith. Gravity is now pushing on it. The otolith moves down. The gel is moving down and pulling the hairs with it. And so you get your receptor output increasing. And of course, the opposite would happen if you tilt forwards. So bending of the hair produces depolarizing or hyperpolarizing graded potentials depending on the head tilt. And then via the vestibular cochlear nerve, the CNS receives different neural patterns depending on the head position. Another example of the utricle is the change in horizontal linear motion. So in other words, forwards and backwards. And this helps to displace those utricle hairs. So again, if we're taking a look at this guy, we're activating the utricles by horizontal linear acceleration. So he's working forwards, and as he walks forward, you can see they tilt in the opposite direction. So the top heavy otolith layer lags behind the gelatinous layer and the hairs due to its greater inertia. So it has a greater inertia. And the hairs bend to the rear in the opposite direction of the forward movement of the head. And if you keep walking, of course, the otolith layer catches up and the hairs are no longer bent. And when you stop, the otolith layer briefly continues bending the hairs forward because it's basically playing catch up before it obviously then comes back into the upright position as well. And the saccule responds to tilting the head away from the horizontal position and vertical linear acceleration and deceleration, as we've already alluded to. So it's important to realize that these hair cells of the utricle detect horizontal directed linear acceleration and deceleration, but they do not provide information about movement in a straight line at a constant speed. And remember, the saccule hairs are horizontal, so they respond to a lift going up and down. They might respond for you jumping out from bed, jumping up and down, and like I said, riding in a lift as well. So what about the vestibular pathways to the brain? What are they? Well, we have vestibular pathways. We're thinking about equilibrium and orientation, and it isn't just about vestibular pathways in terms of equilibrium and orientation and where is my head in space and where is my body in space. You've got these vestibular receptors, which are telling you basically where is my head, what's my head doing. You've got your visual receptors, which are saying, putting it all into context with the environment around you. And you've got your proprioceptive receptors, which of course are the receptors in your joints, for example, which are telling you where are my joints in space. So we've got where is my head in space, where are my joints in space, and where am I? And all of those, all that information is processed together. It goes to the brainstem and it goes to the cerebellum as well as to our conscious awareness. And in our brainstem and cerebellum, there are various reflexes that we have. So one of them is eye movements. Your eyes remain fixed on the same point despite head movements, and that's through your cranial nerves 3, 4, and 6. Another reflex, your vestibular spinal tract, is your balance and posture maintenance to the motor neurons of the limb and the torso skeletal muscle. So, for example, when you're maintaining balance and posture, if you stumble, the body imbalance must be corrected very, very quickly, otherwise we'll fall. Because by the time we would have thought about correcting our fall, we'd already be on the ground. So these vestibular spinal tracts, particularly prominent in reflex movement of the neck, the limb, and the trunk muscles, to help us having a complete crash onto the ground and help us change the way our muscles are contracting and are relaxing to try and make us stay upright. You'd have all done it. You might have tripped on a pavement, and instead of lying splat on the floor, you've actually managed to right yourself without falling, hopefully. Okay, and that's part of those reflex movements. And you've got the perception of motion and orientation. So that's the output that's going to your central nervous system and conscious awareness. So visual inputs, so we've got motion sickness, and these visual inputs indicate your body is fixed with relation to an object. For example, your cabin on a ship. However, your vestibular apparatus detects movement, and these signals disagree with the visual signals, and this confuses the brain, which somehow leads to motion sickness. And it's the same for some people for first-person computer games. The visual signals disagree with the vestibular signals. Okay, so a couple of review questions for you. So press pause and have a little bit of a read, a little bit of a think. There's more than one correct answer, just so that you know. The receptors for dynamic equilibrium provide information about which of the following conditions? Acceleration, correct. Deceleration, Correct. Rotation at a constant velocity? Not correct. Direction of rotation? Clearly that's also correct.